You might be wondering, what exactly is a semiconductor? These are semiconductors. The silicon in the sand can get heated and cut to be transistors that we use in our chips in our daily lives.
Transistors are fundamental for modern electronic devices, and they were introduced in 1947 to revolutionize calculators, radios, and computers. And the two things that they can do is, with a power source, an electric current, it can be amplified to increase the output when given a smaller input, or it could be used as a switch to potentially just stop the signal on and off. And now, it used to be singular transistors, but nowadays they're generally used in integrated circuits through plasma etching, which is one of the major processes for making a microchip.
One of the most significant processes in creating silicon microchips is plasma etching. Plasma etching utilizes the property of semiconductors that allows them to change their conductivity through the process of doping. Doping is creating impurities in silicon to create semiconductor junctions in which electrons can pass through. It starts off with masking the silicon wafers with a type of fused silica glass in areas that you don't want semiconductor junctions. And then plasma is shot at high speeds at the silicon wafer, creating trench-like structures where there is no masking. After the electrons from the plasma embed themselves into the silicon wafer, these trench-like structures become positively charged, while the unaffected areas become negatively charged, allowing electrons to pass through while being repelled by the negative areas around them and attracted by the positive trenches they're passing through.
When materials are doped, there are two different subgroups created, called N groups and P groups. These groups either have a deficit or an excess of electrons. When a current is ran into the base, the electrons move through the other groups, causing the current to amplify. However, when the base of the transistor is less than 7 nanometers, the electrons skip through the base, causing the transistor to break.
Greg, can we make transistors smaller?
Great question, Ben. No, but one of the most popular ways of continuing Moore's law is through use of 3D integrated circuits. In other words, stacked semiconductors on top of each other. The way of doing this that I'm proposing is through alignment and bonding of semiconducting wafers. Vertical connections between the two can happen before or after the alignment and bonding. But rather, the most important part is, rather than spending millions of dollars on shrinking semiconductors that might be virtually impossible to do, I say we build in the third dimension, where we have more semiconductors in the same footprint of space, allowing for much better performance.